Good morning. My name is Fakhar Nadeem, and my dissertation is titled Generalizing EEG-Based Seizure Prediction Across Datasets. The study investigates whether EEG-based seizure prediction models trained in one setting remain useful when applied to unseen patients and to a different public EEG dataset. The focus of the dissertation is not just prediction performance, but also generalization. This figure shows the temporal phases of seizure-related EEG activity: interictal, preictal, ictal, and postictal. My work focuses specifically on the transition from interictal to preictal because seizure prediction aims to identify risk before seizure onset rather than during the seizure itself. This matters clinically because unpredictability is one of the most difficult aspects of handling epilepsy. If a seizure could be predicted reliably in advance, patients could take protective action against it, and future systems could support personalized monitoring or intervention. However, the major challenge is that many published models perform well only in familiar settings, so the key issue is whether these systems actually generalize. The aim of this dissertation was to evaluate whether seizure prediction models trained on one cohort actually generalize both to unseen patients and to an external dataset. The study was guided by three research questions. The first asks how well models work in a patient independent setting within CHB MIT. The second asks how well those CHB trained models transfer directly to Sienna without retaining. The third asks whether limited fine tuning on Sienna can actually improve that transfer. So the study moves from a difficult within dataset setting to a more demanding cross dataset setting. This figure here compares the two datasets used in the study. So CHB MIT was used as the source dataset for model development and patient independent benchmarking. It is a pediatric scalp EEG dataset sampled at 256 Hz. Sienna was used as the external target dataset. It is an adult video EEG dataset originally sampled at 512 Hz. These differences are really important because they introduce meaningful dataset shift. So the transfer experiment is not just another benchmark exercise. It actually tests whether a model trained under one set of population and recording conditions can still remain useful and can actually retain some useful predictive value in a different setting. So here we discuss how the label generation process actually worked. Continuous EEG was divided into 30-second windows with 50% overlap. A window was labeled preictal if it fell fully within the 30 second to 5 minute interval before seizure onset. A window was labeled interictal if it was at least 2 hours away from any seizure. Ambiguous windows were excluded from this. This is important because the study was designed to preserve a genuine seizure prediction task rather than allowing the problem to become seizure detection. The figure shows the full processing workflow. Raw EDF recordings were loaded, channels were harmonized across datasets, and Sienna was resampled to match CHB MIT. Also, signals were filtered and normalized and then segmented into labeled windows. So the figure here shows the cross dataset harmonization step. Both datasets were reduced to a shared common channel representation so that the same model input structure could be used across CHB MIT and also Sienna. This step was necessary for transfer, although it may have maybe reduced some signal detail. This figure also summarizes the 1D CNN architecture used in the study. The three models compared were logistical regression, random forest, and a 1D CNN. The idea was not to build the most complex deep model possible, but to compare a reasonable deep approach against interpretable classical baselines under the same pipeline. These models were evaluated in three stages: patient independent CHB MIT evaluation, zero shot transfer to CNN, and limited CNN fine tuning on CNN. So, this figure here shows the baseline comparison. The classical models did detect some seizure related structure, but overall, patient independent discrimination remained pretty weak. The next figure also compares all models under leave one patient out CHB MIT setting. The key pattern is that the CNN was strongest overall model. At threshold zero point 0.1, it gave the highest recall, F1 score, and AUC. At threshold zero point 0.5, it gave the highest accuracy. So the CNN improved on the classical baselines, but performances still remained only moderate. That means patient independent seizure prediction within a single dataset was possible, but clearly still pretty difficult. Now, this is one of the most important figures in the dissertation. The figure compares patient specific and patient independent performance. The key pattern is that patient specific results were dramatically stronger. That tells us something very important. Seizure relevant predictive signal is clearly present in the EEG. So the disappointing patient independent performance cannot be explained by a complete absence of useful signal. Instead, the main problem is that this predictive signal does not transfer cleanly across individuals. In other words, intersubject heterogeneity is a much bigger challenge than within patient classification. This figure shows the drop in performance when models move from CHB-MIT to Siena. This is the clearest demonstration of dataset shift in the dissertation. The CNN, which had been the strongest within CHB-MIT, transferred poorly in the zero-shot setting. Next figure also shows that limited fine-tuning improved the CNN on Siena. So the source representation was not useless, but it required an adaptation to the target domain. However, the figure following this shows that why this is still not enough for practical use. Even though seizure sensitivity improved, the false prediction rate remained extremely high. So the model became better at identifying seizure risk, but not yet good enough to function as a realistic warning system. Well, to conclude, this dissertation shows that seizure predictive signal is clearly present in the EEG, but robust generalization remains difficult. The CNN was the strongest model within the data source dataset, yet both the patient heterogeneity and the dataset shift caused substantial performance degradation. Limited fine tuning partially improved transfer, but false alarm burden remained a serious limitation. So the main conclusion is this: high seizure prediction performance on one dataset does not guarantee robustness across new patients, new datasets, or new institutions. Thank you very much.